So before I talk about squeeze theorem, let me just do this quick example that we were looking at last time. So first of all, remember, when we look at this, we're classifying it as either, as being a limit problem, as opposed to being a differentiation problem, an integration problem. For integration problem, for a limit problem, the first thing we do now is to try and plug in the limit. So if I plug in x equal to 2, then we get the indeterminate form 0 over 0. So let me remind you of this word here, indeterminate form. So that means it's something in a limit that we don't know what's happening and we need to do more mathematical investigation. Typically our strategies involve multiplying by the conjugate, factoring and canceling, using the squeeze theorem. In this case, we want to look at the one-sided limits. And that has everything to do with the definition of the absolute value of x minus 2. So here, starting with the generic definition of the absolute value of a, by replacing a with x minus 2, I can come up with the definition for the absolute value of x minus 2. And over here in the domain here too, I'm replacing with x minus 2. Then I move this minus 2 over, and we get this formula here for the absolute value of x minus 2. And so at the end of the day, it's important that you can go from here to this step here. And so now I can divide the absolute value of x minus 2 here. I can divide this by x minus 2. I can divide here by x minus 2, top and bottom. And when we do that, we get, this is what the function that we're trying to find the limit of looks like. So here, x minus 2 divided by x minus 2 is just 1. That's where this is coming from. And then negative x minus 2 divided by x minus 2, you cancel the x minus 2s, that just becomes minus 1. And now we know what the function looks like if you approach x from the right or if you approach x from the left. And so now we can look at the one-sided limits. Approaching x from the right, in the numerator, absolute value of x minus 2 gets replaced with x minus 2, and you cancel the x minus 2. So here, don't forget to cancel, and our limit's 1. So cancel the numerator, the denominator, the limit's 1. Approaching from the left, x is less than 2, so absolute value of x minus 2 is minus x minus 2. And now again, cancel the x minus 2 part. I'm left with the limit is minus 1. So finally here, we notice the limit from the left doesn't equal the limit from the right. So the two-sided limit then does not exist. So this right here is my final answer. And as far as for you, if you're doing work, the main work you would have to show is just these two things in these two red boxes. That's the main work you would have to show. I'm just a little more explicit because I'm teaching it. And that's right, Sal. And I'm, trying to explain more because, I'm a teacher. I should probably do that. So just a general comment. This was a special example of this more generic problem. X going to 0, absolute value of x over x. And again, this does not exist for exactly the same reason. It's nice to kind of remember some of these problems that are a little weirder. Just it helps us to remember how to work with limits. So here the strategy when we get 0 over 0 is to look at the one-sided limits and use the definition of the absolute value. So for squeeze theorem, it involves inequalities. So I wanted to very quickly review your properties of inequalities in preparation for squeeze theorem. So for any constants a, b, and c, if a is less than b and b is less than c, then a is less than c. That's called transitivity. B here acts like a bridge. A is less than b, but b is less than c, so a is less than c. If we have a less than b and c is any constant, then you can always add c to both sides without affecting the direction of the inequality. So if a is less than b, then a plus c is less than b plus c for any constant c. And here, you've seen these before. If I have a is less than b and c is a positive number, and you multiply both sides of the inequality by a positive number, the inequality stays the same direction. If you multiply both sides of the inequality with a negative number, the inequality flips its direction. And this is really because of increasing and decreasing functions. When we study these as the properties of inequalities, in the background, there's increasing and decreasing functions. So let me just remind you, if f is an increasing function, then we have this property. A less than b implies f of a is less than f of b. So I did an example here with x squared. If you look at the function x squared for x greater than 0, so this example, I wanted to be a little bit tricky here. So I purposely picked this example. If you look at x squared for x greater than 0, then we have an increasing function. So then now if I have a right here, if I have a and b, you can see f of a will be less than f of b. That's because here x squared is increasing. For a decreasing function, you remember the definition for decreasing, we have the opposite. A is less than b, then f of a is greater than f of b. And here I took x squared again for the example, but x squared where x is restricted here to be less than 0. Remember that you're looking at the graph from left to right. So if you look here, if a is less than b and they're both less than 0, and if you square, then a squared will be greater than b squared, not less than b squared. And compare it with this other one. If a is less than b and they're both positive, then a squared will be less than b squared. It all depends on if I'm in the increasing section, portion of the graph, or the decreasing portion of the graph. Here we're getting two different behaviors depending on which section. This is because it's decreasing, and here this happens because it's increasing. And they're same function, two different behaviors. Because in one region we're in an increasing part, in one region we're in a decreasing part. If you're in a part of the function that's neither increasing or decreasing, then all bets are off. You have to really be careful and check on a case-by-case basis what's happening when you apply the function. Anywho, I'll show you some of these inequality properties at work here in a second. It's really about how do we now use these to answer questions. Okay, so here's the squeeze theorem. So the squeeze theorem, anything that's a theorem is a statement of truth. And a squeeze theorem is typically a conditional statement or a biconditional statement. So it'll have a hypothesis. So here, this is the hypothesis. So it'll have a hypothesis. If the hypothesis is true, then we get the conclusion for free. That's what's nice about a theorem. We just have to satisfy the hypothesis, the conclusion, then we get for free. Here we have two conclusions. So here's the hypothesis. Suppose we have three functions, f, g, and h. And suppose f of x is less than or equal to g of x, which is less than or equal to h of x for all x near a. That's the hypothesis. If that's true, then here's conclusion number one. The limit of the functions will also satisfy the same inequality. That is, if f is less than g and g is less than h, then the limit of f will be less than the limit of g will also be less than the limit of h, less than or equal to. So here, you should think for this inequality, all I did was slap on limits. I just wrote in the limit right here. I wrote limit, blah, blah, blah. I just wrote in limit, da, 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 and just limit. Just followed the exact same inequality, just slapped on limits. Now, here's the second conclusion. The second conclusion is if this limit on the left side here converges, goes to some finite number, call it L. And if this other limit here on the right-hand side here also converges to that same finite number L, then the limit in the middle, because it's always in between these two, it has no choice but to also converge to the same number L. And that's what the squeeze theorem basically says. The limit of f of x goes to L and the limit of h of x goes to L, where L is a real number. Then in between, the function g has to also go to L. And basically, it's being forced are squeezed by the function on its below it and the function above it. So here's the function below and the function above, and g is stuck in between. And you look, when we take the limit as x approaches a from either side, you see what happens to the limit. It's getting pinched or squeezed. And so usually the way a squeeze theorem problem works is we're trying to find this limit in the center. Usually we want to know what's going on with this limit in the center. And so, sometimes we can't do it directly, so we'll have to use a squeeze theorem to solve the thing. Some people do also call it the sandwich theorem. So there's a question, is the squeeze theorem the same as the sandwich theorem? And it is. I just call it the squeeze theorem, because why can't I make it stop doing the question marks? Okay, so I just call it the squeeze theorem just because that's what I learned growing up. So here are two kind of variations of the squeeze theorem that you don't hear about very much. So what was in the green box, this is using squeeze theorem. This is a scenario where squeeze theorem gives us convergence, but there are scenarios where squeeze theorem can also give us divergence, or where the limit doesn't exist. So here's one situation. So suppose f is less than g, and suppose we know the limit of f goes to infinity. So here, if g is bigger than f and f is blowing up to infinity, then the conclusion is that g must also be going to infinity. So this is our conclusion here in this scenario. If f is less than g and f is blowing up, then g has to also blow up. And in this case, we would conclude the limit of g doesn't exist. And this would be a squeeze theorem that we just used. And another similar scenario is, so if we know f is less than g, and we know the function g is going down to negative infinity, it's plunging. So here, f has to always be less than g, but g is going to negative infinity. So in this case, the only conclusion must be that f is also going to negative infinity. That's the only way, f can be less than g if g is going to negative infinity. The only way f can still be less than or equal to g is if it also goes to negative infinity. So we'll come across these later, not necessarily right now, but I just want you to keep these in mind, that there are ways. This is also a variation of squeeze theorem. Usually what's in the green box is typically taught as squeeze theorem, but there's also these subtle variations. Finally, using the squeeze theorem, there's a very important limit. There's two important limits, but this one is the more important one. So there's the limit of sine of x over x as x goes to 0 equals 1. That's an important limit. And a second important limit, but not as important, is the limit of 1 over cosine x. The limit of 1 minus cosine x over x as x goes to 0 is equal to 0. So this limit right here, I'm going to ask you to memorize. The cosine one, you don't need to memorize. It's done as an example in the book, example 11. You might want to read it just to practice the math, but this limit here is definitely important. So this limit, you should definitely, memorize. The sine of x over x as x goes to 0 equals 1. Remember, if you try to evaluate this limit, you get 0 over 0. So I'll show you how we use this squeeze theorem to work out this limit in a second here. Okay, let's do some quick squeeze theorem problems. So this first problem is kind of too easy, but I wanted to start slow. So here we're asked to find the limit of some function g of x as x goes to 0. We don't know what the function g of x is. In this problem, they haven't told us what g of x is. The only information we know about g of x is we're given that g of x satisfies this inequality. And so in this scenario, given an inequality that g of x satisfies, and given that we're trying to find a limit, the only option left to do is to try squeeze theorem. So here, by squeeze theorem, I know if the function satisfies an inequality, the limit of the functions will satisfy that inequality also. So here, from here, I just added the limits. Now, for squeeze theorem to work, I need to check that this limit here on the left side and the limit here on the right side, the limit of 2 cosine x as x goes to 0, I need to check that those go to the same number. For 2 minus x squared, we can use the direct substitution property because 2 minus x squared is a polynomial. I can plug the 0 right in. So when I plug in 0, we get the limit is 2 minus 0 or just 2. For the other limit, we can plug in points closer and closer to 0. And we get the limit is 2 times cosine of 0. Cosine of 0 is 1. So here, both of these limits are going to 2. So the limit in the middle, by squeeze theorem, has to also go to 2. And so, you know, the important part of a squeeze theorem argument is to give the inequality, do the limits, and then make your conclusion. And don't forget to shout out the squeeze theorem. So the stuff that's highlighted and the stuff in the red box, that would be the core stuff that we have to see for squeeze theorem argument. What's the inequality? Calculate the limits of the functions at the left and right side, and then make your conclusion. And you know, if the limits aren't the same, then we have to try something else. So I wanted to do a slightly more complicated problem. So with this problem, first, let me warn you, we haven't done a limit like this, where pi over x as x goes to 0. We haven't done a limit like that. But I can show you, we'll see in section 1.6, that such a limit, if you check the graph of this function, the graph looks like this. The graph of pi over x, okay, just this part. Just this part. The graph looks like this. It's just a rescaling of 1 over x. So as x goes to 0 from the right, the y function goes to infinity. And here, cosine of infinity, think about the cosine graph. Cosine just oscillates forever up and down. So the problem, mathematically speaking, is that this limit does not exist, which makes us wonder, well, then what's going on with this limit? Because we're not sure about this part. This part of the limit doesn't exist. When x goes to 0, cosine of pi over x doesn't exist. So we're not, so that's why we need to do more math here. That's why this is not, you know, just easy problem, just apply the limit. So here, because the cosine of pi over x limit doesn't exist, the original limit that's given to us is indeterminate. We're not exactly 100% sure what's going on with this. We can guess. Here's a very valid guess. I could say, hey, this function cosine, this is a bounded function. It goes always between -1 and 1. And this function x squared, it's going to go to 0. So this will be 0 times a function that goes between -1 and 1. The limit will be 0. And that logic is perfectly valid. The issue is when we try to write that up in a mathematical form. That explanation I just gave is actually a verbal explanation of the squeeze theorem. To write that explanation mathematically, we use the language of squeeze theorem. So first, I'm going to start by establishing an inequality. Okay, the easiest way to establish an inequality is to start with an inequality. And here, one thing we know about just cosine by itself is we know cosine is always between -1 and 1. And the function we're dealing with is not cosine by itself, it's cosine times x squared. So now I'm going to multiply in the x squared. So here now, when I multiply in x squared, we get negative x squared is less than equal to x squared times cosine pi over x is less than x squared. Remember, x squared is greater than or equal to 0, so we don't need to reverse the direction of the inequality. Well, you know, now we've got our inequality. In terms of squeeze theorem, I've got my inequality. So now I know the function satisfies an inequality, the limit of the functions will satisfy an inequality. And so now all I have to do is evaluate these limits here at the end. So this limit here and this limit here, if they go to the same number, then we've squeezed the limit in between, right? If they go to the same number, then this limit in between will be squeezed. Now, obviously, you can tell from looking at those limits, they go to 0. You can think about the graph where you can plug in numbers. The limit of negative x squared and the limit of x squared as x goes to 0 from the right is equal to 0. So the limit in the middle has to also be equal to 0. And so my final answer is the limit is 0, and then by squeeze theorem. It's important to shout out squeeze theorem when you use squeeze theorem. Here, I know I shouted it out twice, but that's just how I am. That way, for sure, no one can take off any points. So with squeeze theorem, you kind of have to first recognize there's something weird happening with this limit and we need to try something. And depending on the scenario, especially if there's a trig function involved, if there's a sine or cosine involved, then probably there's some squeeze theorem potentially, you know, if it's not a limit that just doesn't work right away when you plug it in. Because cosine and sine give us an easy place to start establishing an inequality. You know, usually it's not that easy to establish an inequality. All right, I want to do this sine of x over x problem. So this is a very tricky problem. I don't expect, you know, students to be able to just do this problem. So what I do expect is for students to know this result. At the end of the day here, I'm going to ask you to memorize this result. But I'm reluctant to ask you to memorize it without justifying it a little bit. So I want to show you a little bit of a proof and show you how the squeeze theorem works. So the book does a proof. The book's proof is much, much more complicated. I feel like this proof is a little more accessible and easier to understand. So the strategy of this proof, we're first going to show the limit from the right equals 1. And then I can use some geometry tricks to show the limit from the left going to 0 is also 1. And then we'll have the two-sided limit. Okay, so I'm first going to show the limit of sine of x over x as x approaches 0 from the right is equal to 1. So here I'm going to motivate it with a graph. Okay, so this isn't necessarily rock solid as far as proofs go, but I think it helps the intuition. So here I've graphed y equal to sine of x and y equal to x. But I only need the graph in the first quadrant. So I actually have only graphed, you know, y equal to x, y equal to sine x in the first quadrant. Now, if you look in the first quadrant for x to the right of 0, but very close, you can see y equal to x is greater than sine of x. In this section here, sine of x is less than or equal to x, you can see. In this whole section here, approaching all the way to 0. So divide both sides by x, and I get this inequality. Remember, I'm trying to do a squeeze theorem. So what I really want to do is get sine of x over x in between, you know, in an inequality. So this is half of it. I have sine of x over x is less than 1. Now I need sine of x over x bigger than something to establish our inequality. That's where the second graph comes in. If you look at the second graph, so here what I've done is I've graphed the tangent, so that's y equal to tangent x and y equal to x. Again, I only need those graphs in the first quadrant. And again, if you look at the graph shows for x greater than 0, but very, very close, the tangent curve lies above y equal to x. Tangent of x is greater than x. So now rewrite tangent as sine over cosine. And then cross multiply, exchange the position of the x and the cosine x. They're both positive. Here, x is on the right side here, so x is positive. And if you think about cosine, very close to 0, on this side is also positive. So we can cross multiply without moving the inequality. So look here, this says sine of x over x is greater than cosine. This says sine of x over x is less than 1. So we can put both of these together. and come up with an inequality that'll allow us to, do squeeze theorem. So here's my inequality when you put both of those together. Sine of x over x is less than or equal to 1, and sine of x over x is greater than or equal to cosine. So now hit everything with a limit. So now we hit everything with a limit. And the limit of cosine of x as x goes to 0, you plug in points, this goes to 1. This goes to 1. And the limit of just the constant, 1, it's a constant. So the limit here is always 1. So by squeeze theorem, the limit of sine of x over x as x goes to 0 from the right will be 1 by squeeze theorem. So for the other part, and I'm not going to really go into detail, but basically we can show that sine of x over x is an even function. And so by the symmetry, we can show the limit approaching 0 from the left is also 1. So let me just draw you a quick picture. So I laid it all out here, but I don't want to go through the math, and you can go through it. And again, you're not responsible for this. I just wanted to, before I ask you to memorize the theorem, I just wanted to give you some justification. So here, let me do a geometric justification now. So look, what we've established is our function, when it approaches 0, so we're taking a limit approaching 0 from the right. I don't know what the graph is, but I know that as we get closer and closer to 0, the function is approaching 1. This is the number 1. And we will be able to show that this function is an even function, okay? It's because sine of x is odd, x is odd function divided by odd function gives you an even function, okay? So when we remember, for an even function, it's symmetric about the y-axis, so the graph is just going to be the reflection. So if approaching from the right, it goes to 1, then because it's even, when we approach from the left, it'll also go to 1. So here I prove this, up here I'm proving the function is even. And then down here, I show the limit as x approaching 0 from the left equals 1, using a change of variables. Again, all of this you're not responsible for. This is just, so I have some math before I ask you to memorize the formula. At the end of the day, we conclude that the two-sided limit of sine of x over x as x approaches 0 is equal to 1. And that's the information you should memorize. You don't need to know that proof I just did. If you can follow the steps, that'd be great. But at the end of the day now, this is the main information we need to memorize. Okay, folks? And when I say this is the main information, what do I mean by that? Okay, good stuff. What do I mean by that? Don't be, never mind that this is the x variable. And this is, I don't care that it's an x variable. Here's what I mean when I say you should memorize this result. What you should memorize is the limit of the sine of blah divided by blah will equal 1 if blah goes to 0. All that matters for this limit is that this expression in the sine and this expression in the denominator are the same and that they're going to 0. That's all that matters. If the argument of the sine and the term in the denominator are the same, and if they're going to 0, then the limit will be 1. Okay, that it's actually an x variable doesn't matter. Just that whatever is up here needs to be the same as whatever's down here. That's what's important. And the second thing is they're both going to 0. That's what's important. So I'm going to do some examples here in a second, but I just want to mention one final comment here that the value of the function at the point is different from the value of the limit of the function at that point. In this case, the function's not defined at 0, so f of 0 is undefined, but the limit of f of x as x approaches 0 is defined. Okay, so, and of course, in this scenario, we can fix it. We could define a new function. We could just let it be sine of x over x as usual when x is not 0, because there's no issue away from 0. And at 0, we could define the function to be its limit. Its limit was 1, so we can define it at 0 to be 1. And then this new function will have this property that its limit exists at 0 and the function also exists at 0, okay? But f of x by itself, if you don't fix it, then f of 0 is undefined while the limit exists. Okay, folks, I'm now going to use this limit, which we now is fact in this class. We no longer have to prove this limit. From here moving forward, the fact that sine of x over x as x goes to 0 is equal to 1, that'll be just a known fact in this class, okay? So I want to now do examples using this new, identity basically that we've discovered. So you cannot use L'Hopital's rule. So Sal asks if we can use L'Hopital's rule. You cannot use L'Hopital's rule until the very end of the semester in chapter 5. I mean, you can use it to show this limit, but you can't use it like in class yet because we haven't studied it yet. My bad, y'all. So, okay, for this limit, honestly, this is not a difficult limit. If down here we had a 6, we'd be in business. Because when x goes to 0, 6x goes to 0 in the numerator and 6x goes to 0 in the denominator, we could say, we could evaluate a limit. But the problem is I don't have the 6 down there. So we're going to use some algebra now and manipulate it. First, remember this is a limit. So the first thing to try is to substitute. When you plug in a 0, you get 0 over 0. And so we have to try something. Here, because of the form, because it's sine of something over something, I want to try and take advantage of this identity, right? We know now that this is always true. Okay, so I'm going to make the given limit look like this identity that we have in the red box. So I did this a little more technically than you need to. I did a variable change, but you don't need to, okay? I'll show you the work you would need to do. So here I say let theta equals 6x. Then if x goes to 0, theta goes to 0. And now here I'm going to change everything. So look, here's my original problem. When I plug in 0, I get 0 over 0. So here's the part that's really important that you should do. So now I want the denominator to be the same as what's happening inside 6x. So I multiply the bottom by 6 and I multiply the top by 6. That part is really the part you need. And so now, here if you want, like I said, I use the different variable, but you can replace the 6x here with theta. You can replace this 6x in the denominator with theta. And as x goes to 0, theta goes to 0. So I can replace this part. And so now I get a limit that looks exactly like the limit we know from squeeze theorem. And so this, as theta goes to 0, this limit will go to 1. And so my limit here is 1 times 6 because I still have this 6 hanging around. For you, you can skip this part. You don't need to do the variable change. This part's not necessary. You don't need to do the variable change. This is perfectly good, and this is what I would expect, to see. This is perfectly good. So here what we're doing is first, we realize there's an issue. Then we multiply top and bottom by 6 to keep the equation balanced. And now for the limit, look, this 6x is the same as 6x. And as x goes to 0, in here, this goes to 0. This goes to 0. So using our special theorem, using this special result here, you can say this whole thing goes to 1. You don't have to use the variable change. I wanted to be very explicit because I'm teaching it. And I wanted to show every single step. So that if someone really wants to know every detail, it's right here. But, for you, like I said, if you can see the concept, And here go, oh, you know what? I need the same thing on the bottom. So let me divide by 6. Let me multiply by 6. And now this limit just goes to 1. And you can evaluate the limit, get rid of the limit, you know. Okay, this next one, it's the same thing. You know, if you look at it, it looks kind of complicated, but it's not. So here, if you notice, this x squared minus 1 is the same as what's being divided down here. Perfect. That's good. That's already starting to look like this part. We got sine of blah divided by blah. Now look, when x goes to 1, x squared minus 1 goes to 0 in the sine argument and in the denominator. That's the same thing that happens with our identity that we memorized. You know, when you send theta to 0, this argument of sine and the denominator is going to 0. So this limit actually just equals 1. First time plug in, because that's always what we try with a limit, try and plug it in. In this case, we'll get 0 over 0, indeterminate form. But because there's a sign involved, you know, sometimes there's a little bit of trial and error, but here, because of the form, I can guess we're going to use this special limit. Again, I did a variable change, but you absolutely do not have to. So here I say let theta equal x squared minus 1. So I'm replacing this entire expression, x squared minus 1, with theta. I'm just making that into a single squiggle. And I also notice that when x goes to 1, theta goes to 0. So I end up being able to rewrite this limit so that it looks exactly like our identity, you know, that we have. So here I'm able to rewrite this limit so that it looks like, again, you can skip that step. And then this limit goes to 1. So you know, if a student wrote this and then just gave a little bit of justification. So here mention something about the special limit, mention some, you know, by the special limit sine of theta over theta. And if you did that, I'm happy with that. I think that works. You know, you don't need to do this variable change if you don't like it. I just want to be very explicit so that people can see all the steps and exactly connect it up back to our theory. So here, this next one, let me do this last one, and then we'll go to talk about continuity really quick. Here, if you plug in 0, you get 0 over 0. And because of the signs, you know, the sine functions, I want to try and use our identity here. So now the trick is just algebraic manipulation. Look, I break it up. In the denominator here, I need a 6x. And in the numerator here, I need a 3x. But I have to make sure my equation stays balanced, right? So I divided by 6x here. I multiply top by 3x. Now let me check that the equation has stayed the same, right? When I multiply everything, I better get back the same thing. The x's are okay because the x's cancel. Here I have a 3 over 6, which is 1/2. So I multiply by 2 to balance it out. Basically, this is a convenient 1, you know, one of those things. I'm just making sure everything is balanced. So here now, if you multiply everything out, 2 times 3x will cancel with 6x. We'll get back what we originally started with. So now we're almost ready. This part looks exactly like our special form right here. I just need to do one last thing here. This almost looks correct, but it's the reciprocal. So that's okay. We have limit properties. I can write this term 3x over sine 3x as 1 over. Now this part in the denominator has exactly the same, has exactly the same form as this. So when I apply the limit, this is a special limit. This will go to 1. And here in the denominator, this is a special limit, which will go to 1. Both, you know, by squeeze theorem we proved. And so my final answer here is 1 times 1 over 1 times 2, or just 2. And so certainly with this last problem, I didn't do any of the variable changes that I did in the previous problem. And you know, this is kind of the way I would expect a student to do this problem, not necessarily putting any variable changes, but making sure they've got a balanced equation, making sure that what's in the argument of the sine is the same as, what's being divided or what's on top here. These have to be the same. And then if those go to 0, you can apply the special limit. That ends section 1.4. So I want to switch over now and talk about continuity and just give you the definition. So we've actually seen continuity already. It's just the book called it the direct substitution property. So I just want to mention, when we talk about continuity, that pertains to limits of a function. That's about limit behavior of a function. So here, if we say, the definition here, we say f of x is continuous at the point x equal to a, if and only if this is true. It's a limit definition, that the limit as x approaches a of f of x has to equal f of a. The way I like to think about it is that continuity allows us to take the limit and bring it inside the function. And now when you take this limit, the limit is of x as x approaches a, that gets you to f of a. So continuity allows us to bring the limit inside the function and put it right on the x variable, which makes doing limits really nice and easy. And the book referred to this in the previous slide, in the previous section, as the direct substitution property. Now, when we make this statement, we're saying 3 things, and it's very important. We're saying, number 1, that the right-hand side is defined. We're saying f of a is defined. So in particular, we're saying that x equal to a is in the domain of f. The other thing we're saying is that the left-hand side, the left-hand side here is defined. What does that mean? It's a 2-sided limit. So that means the limit from the left equals the limit from the right, and they're both equal to some finite number. So remember, that's all our limit theory. So when we say the limit exists, we're saying a lot. It's a 2-sided limit. So we're saying the limit from the left exists, the limit from the right exists, and they're both equal a finite number. Finally, the third thing we're saying is that the left-hand side equals the right-hand side. Right? The final comment is that we have equality between these two. So the left-hand side's defined, which is great. The 2-sided limit on the right-hand side is defined, which is also great. But now these two are also equal. That's the third piece of this equation. Okay, so it's important that you understand all those implications here. It's a simple equation, but really it's there's a lot going there. You have to unpack it. So we have this concept of continuity from the left or the right. So continuity from the left is if the limit of f of x as x approaches a from the left equals f of a. So this is used at endpoints. So continuity from the left or right. So continuity from the right, basically the same continuity definition, but instead of doing a 2-sided limit, we're doing a 1-sided limit, and this is a limit from the right. So here we define 1-sided continuity at endpoints. And at endpoints, you may not be able to do a 2-sided limit. So at an endpoint, it might be continuous from the left or continuous from the right if the limit of the function and the function value are the same. A function is continuous on an entire interval, not just a single point. On an entire interval, if and only if it's continuous at all the points in that interval. So if I say a function is continuous on the real numbers, I mean it's continuous for every real number. And what do I mean by it's continuous? That this is true. If I wanted to find the limit of the function at any real number a, the limit is just f of a. That's what continuity says. Finally, if this limit fails, if limit of f of x does not equal f of a, then the function is not continuous at that point, or the technical term we use is discontinuous. If this limit property here, if the limit of f of x as x approaches a does not equal f of a, then it's said to be discontinuous. So now we have some nice theorems, and this is facts that we've known, but now we formally know it, that polynomial functions, rational functions, root functions, and trig functions are all continuous. Let me say that again. If f of x is a polynomial function, rational function, root function, or trig function, and if I'm trying to find the limit of f of x as x approaches a, all I have to do is plug in the a. I don't have to pick numbers closer and closer, none of that. Just plug it right in. So it makes calculating limits really easy now. And again, we have, if f and g are continuous, then the sum and difference will also be continuous. If f and g are continuous, then the product will be continuous. And if f and g are continuous, then the quotient f divided by g will also be continuous, provided we're not dividing by 0. And just more generically, we could just say it this way, that sums, differences, products, and quotients of continuous functions will once again be continuous at any point in their domain. And it's true for compositions as well. If f and g are continuous, then f composed with g and g composed with f will be continuous. And in general, we could say it this way. In general, the composition of continuous functions will once again be continuous on their domain. That's the most important part, right? For continuity, first and foremost, f of a has to make sense, so we have to be in the domain. So that means a is in the domain. So first and foremost, continuity can only occur in the domain of the function. So if you put that all together, then basically sums, differences, products, quotients, and compositions of polynomials, rational functions, root functions, and or trig functions will always be continuous in their domain. Let me just talk about types of discontinuities, and I'll stop here. I've got 4 minutes left. So there are basically 3 types of discontinuities, 3 ways a function can fail to be continuous. The first way is called an infinite discontinuity. This is if the limit as x approaches a from the left equals plus or minus infinity, or if the limit as x approaches a from the right equals plus or minus infinity. They don't both have to be plus or minus infinity. Just one limit from either the left or right side needs to blow up to infinity or go to negative infinity, and that's all that's necessary for us to have an infinite discontinuity. So here in this picture, there is an infinite discontinuity at a. This picture is weird because from the left, coming in from the left, the function is left continuous at a. But coming in from the right, the function has an infinite discontinuity coming in from the right. It's an infinite discontinuity. It's also a vertical asymptote. And I purposely did this weird function because people always say, a function can't cross its vertical asymptote. Actually, that's not true. So the other type of discontinuity is known as a removable discontinuity. So here, in a removable discontinuity, the limit exists, but, the limit exists, but the function does not equal the limit. So right here is our removable discontinuity, where you can see the limit from the left and the right are perfect. They exist, they're going to the same number, but the function at the point is not the same number. Now, for a removable discontinuity, the function does not have to even be defined. Here for this example, I just defined the function at the point, but if the function's totally not defined, that's still a removable discontinuity. The limit exists, but the function doesn't equal the limit. Our third and final type of discontinuity is called a jump discontinuity. This is when both limits are finite, but they're not equal. And so we have a jump right here. You can see the limit from the left exists, the limit from the right exists, but they're not equal. There's a jump. And so for these two, for the infinite discontinuity and the jump discontinuity, there's nothing we can do about it. The function stays broken. But for the removable discontinuity, we can fix that. Removable discontinuity isn't so bad. we can redefine the function at a single point and fix the removable discontinuity. The other two discontinuities, those are, it is what it is. If you get those, that's just part of the function and there's nothing we can do to fix it. Also, by the way, just notice here, at C, the function is right continuous at C because the limit of f of x as x approaches C from the right equals f of x because I colored it in. So it's left continuous at A, right continuous at C. It doesn't have two-sided continuity. It's not, it's not continuous at A, B, or C. The two-sided continuity fails miserably. All right, folks, I'm going to stop here. The next thing